So what's up guys, this is the Round Bottom Flask and welcome to the video lecture series on the electronic structure of atoms. This video is the part 1 of the 4-part series of lectures for this topic. In this video, we will discuss the nature and properties of light. Now, before even the concept of the dual nature of light was even proposed, Newton postulated that light is composed of tiny particles called corpuscles. Now, several centuries later, this was proven by Einstein's discovery of the photoelectric effect. So, if you see it here, this is not the general description. This is the general setup that Einstein used to further prove the nature of light as a particle. Now, light when it strikes a metal surface, when that light is sufficiently energetic enough, if it has enough energy, it is able to eject electrons out of the metal surface. Now, these electrons ejected are detected by this positive terminal, which is further detected by a presence of a current. Now, this phenomenon of the ejection of emitted electrons by the presence of light due to incident radiation of light is what we call as the photoelectric effect. Now, this phenomenon will only occur if light is actually a beam of particles, which further supports the particle nature of light as previously proposed by Newton in the recent years. Now, several years, or rather, we go back in time before the discovery of the photoelectric effect. This concept of light as of corpuscles was briefly trashed by Young's double slit experiment. Now, in Young's double slit experiment, it shows that light is actually a wave, or specifically, it is an electromagnetic wave. This is proven by their double slit experiment. Now, if you have an X-ray source here, and this X-ray source has a couple of barriers with slits on them, which is at the end of the second barrier is a photographic film. Now, if light is actually a beam of particles, when the beam of light passes through the first slit, it will not be able to show on the second slit. However, in the experiment, it shows that on the photographic film, there were dark and light spots. So we know that in the photographic film, when it is exposed to light, there will be some light spots. So there are actually dark and light spots here on the photographic film. Now, these dark and light spots indicate that something here is happening. Now, if the light does not behave as a wave, no spot shall develop on the photographic film, but there are spots that develop on a photographic film. Now, this is only possible if light diffracts as it passes through the slit. So what do we mean when we say diffraction? So diffraction is the ability of light to be slightly bent when it passes through a small orifice or a small hole. Now, imagine instead of this X-ray source, imagine that are ripples of water. If you notice in your ripples of water, when you place a barrier where only a small slit is visible, or rather a small slit is the only way that a ripple can pass through. If you notice, that ripple, when it passes through the small slit, will also form new ripples emanating outward. So that also happens to, and we know that ripples are also waves. So that means that is how diffraction occurs. Now, if there are spots that form here that mimic the diffraction similar to the ripples, that means light is actually a wave. So let's recall that light is proven to exhibit both wave-like and particle-like properties. So what does that what can we conclude from that? So before we proceed to that conclusion, let us discuss first what are the properties of light as a wave. I'll leave that for you to think. I will give you the answer at the end of this video. So the properties of light as a wave, obviously all waves have a wavelength. Now, light is specifically light is a transverse wave. When you say a transverse wave, it goes up and down its axis, or it does not go parallel with respect to its axis. It goes perpendicular with respect to its direct axis of direction. So I finally found the term. So hindi pala siya axis lang, it's axis of direction. So if the wave goes here, a transverse wave will move up and down. So dapat it moves perpendicularly to the direction where it radiates to. Okay? Now so obviously light has, as a transverse wave, it has a wavelength which is just the distance between the two consecutive peaks of a wave. So for the measurement of light, it can vary. It can be from meters to angstrom, depending on the type of electromagnetic radiation. So another is the frequency. So the frequency is the number of waves it can produce in 1 second. So the more general definition of frequency is the number of cycles a motion or a phenomenon or an event can perform in 1 second. Now, in a transverse wave, such as electromagnetic radiation or such as light, one cycle will be from one wave to another wave. So one cycle is actually from here going down, then going up, or from down, up, down. That is what we meant by one cycle. Now, frequency refers to if at a certain period of time, or let's say 1 second, how many of these waves can it actually produce? Okay, and that is measured in the units of hertz, which is equals to cycles. Now, frequency is inversely proportional to the wavelength. It's because that if you're given a certain amount of time, the shorter the wavelength, the more waves that you can produce, right? So for example, this pan here, for example, let's say this line here is from 0 second and this is from 1 second. So for letter A, which has a larger wavelength, from 0 second to 1 second, it can produce 1, 2, 3 waves. For letter B, which has a shorter wavelength with respect to A, so it can produce 1, 2, 3, 4, 5, 6, 7 waves, while letter C can produce 1, 2, 3, 4, 5, 6, 7, 8 9, 10, 11, 12, 13, 14, 15 waves. So if you can see, the shorter the wave that you produce, the more waves that you can produce in 1 second. So imagine 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 if you have a rope tied to a wall and you're holding the other end of the rope, then you try to make waves on the rope. If you notice, if you try to whip the rope faster, more waves it can produce more waves, but at the same time, the waves that you will be producing when you whip that rope will be shorter. So the same analogy can also be applied here. I hope you get what I'm saying. Lastly, one of the properties of light as a wave is speed. So the speed of light, or the speed of every electromagnetic radiation, will be the same regardless of its wavelength and frequency. Now in vacuum, light travels at the speed of 2.9979245 times 10 to the 8th meters per second, or if you've learned your significant figures, the rest of the figures is not significant because of the very large value of the speed of light. We can actually round this off to 3 times 10 to the 8th meters per second. Now, the speed of light rather is equal to the frequency of the light multiplied by its wavelength. Obviously, when you use this formula, your frequency and wavelength should have the same units. So for example, if your frequency is in hertz, your wavelength should be in meters. So if it's in, let's say, megahertz, so it should be in megameters, so on and so forth. So light is not there are actually different types of light, and that different types of light can be differentiated by their frequency or by their wavelengths. Now, a complete list of those electromagnetic radiation is what we call as the electromagnetic spectrum. So in the electromagnetic spectrum, it shows you all of the range of frequency of electromagnetic waves electromagnetic waves that we have discovered so far. So as far as I know, this was not updated for for several decades. So we just assume that we have already discovered all of the possible wavelengths in the electromagnetic spectrum. But obviously that remains to be seen, because who knows, we might discover a technique or a device that can detect far more longer or far more shorter wavelengths than the one in our electromagnetic spectrum. Now, in the electromagnetic spectrum, we can only see a very, very small portion of that. And that portion of light that can be seen, the electromagnetic spectrum that is visible to the naked eye, is what we call as the visible light. So that visible light is a representative of your colors of the rainbow, from red to violet. Now based on the photoelectric effect of Einstein, which he discovers that light carries also energy, so this energy or these particles, which is now called from corpuscles to photons, contain energy equal to E is equals to h mu, or hc over lambda, wherein h is our Planck's constant, which is 6.626 times 10 to the negative 34 joules per second, and c obviously is our speed of light at meters per second, Lambda is our wavelength at meters, and nu is our frequency in hertz. So what is the answer? What is what do you call this? So to answer the question between whether light is a particle or a wave, the answer is it is both a particle and a wave. So it can be concluded that light is a beam of photons, which is the small pockets of energy, or what we call as the small particles, moving in a wave-like manner. So again, from the term of Einstein corpuscles, it has been changed into photons, which is the term that we use today for the particles in carrying radiation particles in electromagnetic radiation. Now this formula is proposed by Max Planck in the 1900s, long before the discovery of the photoelectric effect, based from his observations on hot objects that glowed at a certain temperature. Now he further proposed that electromagnetic radiation from an atom can only be emitted at very specific values. So that is what we call as that very specific values are what we call as quantized values. Okay. To compare, to rather a better analogy on how to describe quantized energy. So imagine a person walking up the ramp. Now, if you notice, the person walking up the ramp, it walks at a continuous pace or a continuous manner. So that is what we call as a continuous energy. Quantized energy, on the other hand, is analogous to a person walking up the stairs, because the potential energy of that person increases at very specific manners, because remember that potential energy, review lang sa inyo physics 1, is equals to mass times gravity times height. Okay? Mass times gravity times height. Now since the height of each step step of the stairs is even, so as you go up the stairs, the potential energy increases at also a stepwise and very specific values. Now you cannot go half a step of the stair, right? Hindi pwede na dito na kapag aakyat ka sa susunod na step hanggang dito ka lang. Okay, dapat dito ka talaga tutungtong, di ba? So that is what is meant by quantized energy. Okay? Or quantization of energy. Now, this means that based on the observation of Planck, that matter can only emit and absorb light energy in whole multiples of h nu. So it can emit energy. So the light energy emitted of a specific atom is equals to n h nu. So n can be any whole number. N can be 1, 2, 3, so on and so forth, as long as it is a whole number. Okay? So I hope you understand the discussion of the nature of light, and I hope you learned something from it. So this is the end of my video. Tune in for more videos to come, and once again, this is the Round Bottom Flask. Don't forget to subscribe to our YouTube channel. See you guys.